Hello everyone, my name is Zachary Jerome, and today I'm going to be talking to you about my summer undergraduate research experience at Florida, also known as SURF. My research primarily focused in transportation engineering at the University of Florida Transportation Institute. If you have any questions or want to know more information about what you see in this video, my email address is provided below. A brief introduction about me and more about my SURF experience. I attend the University of Tennessee, Knoxville, and hope to graduate in civil engineering next May. My SURF program was in the College of Engineering at Florida in the School of Sustainable Infrastructure and Environment. My faculty mentor was Dr. Lily Eleftheriou, and my PhD mentor was Dr. Prithvi Manjunatha. This slide shows some highlights of my SURF experience. The three main one was the autonomous vehicles at intelligent intersections and advanced networks, which I'll explain more in detail. And then the NCHRP 1557 project and the Automated Vehicles Symposium 2019 in Orlando, Florida. AVIAN is a project at UF where it combines multiple disciplines, computer science, mechanical engineers, and transportation engineers to explore different ways of increasing mobility at connected and automated vehicle intersections. We're interested in as we transition to automated vehicles, there'll be a lot of mixed traffic environments. So this project is primarily focused with how do we incorporate conventional vehicles and autonomous vehicles all at the same intersection, where not all of them might have the same connective capabilities. And the primary intersection of interest shown in this figure to the right is at Gale Lembren and Stadium Road. And this is Weil Hall, where the Transportation Institute is located. So the part of that I was working on was in the Python script, the real-time intersection optimizer called the RIO. And this is part of AVIAN that optimizes the intersection to decrease total travel delay. And RIO sends trajectories to CVs in real time every second. For this experiment, what I was working on, we assume that all vehicles are connected and execute the trajectories perfectly. It's important, it's easier to start at an intersection where all the vehicles are automated. There's a lot less, you know exactly what the vehicles are going to do, and you can tell each vehicle what to do. So for what I was trying to do, which was to investigate methods on how to decrease total travel delay, that's primarily what I used, assuming that all vehicles execute the trajectories. And I enhanced the code or added some capabilities that allowed it to plot the executed trajectory. So this figure on the right shows a sample plot of what my code was able to output. And it also calculated total travel time delay. So the way we define total travel delay for each vehicle is, you see here, if the vehicle was traveling at the speed that it arrived at all the way to the intersection, and assuming the intersection was green when it got there, that's the time it would leave. So in essence, it doesn't stop the intersection. Delay is calculated by the time that it could have arrived at the intersection to the time that it actually did leave the intersection. And my script was able to calculate the total delay for all the vehicles here and output them. And then I was also able to refit the code so that I could run multiple different simulations. And in that way, I was able to easily find the optimal minimum distance to stop bar. A little bit more on what the minimum distance to stop bar is, and also the detection range. And these were the two different inputs or values that I was manipulating in order to locate the optimal point or the least travel time delay possible for a given traffic scenario. The minimum distance to stop bar we define as where the computer or the RIO stops computing new trajectories for that vehicle. So once the vehicle passes that line, the program no longer gives it trajectories. That's the route it's going to take throughout the whole thing. So there are benefits and drawbacks to having it too close or too far. If it's too close, it becomes a lot tougher for the vehicle to implement that trajectory. So say if it was 10 meters away and you give it instructions 10 meters, to all of a sudden stop when it was planning on going through the intersection, that can be very difficult for the vehicle to execute. And then also this increases the number of computations the RIO has to calculate. So, the more time it has to detect that vehicle and give it trajectories, you're increasing a lot of computations that the system has to go through. Now, if it's too far, this limits your options as to how optimized the intersection can be. You're sending the vehicle the final trajectory really far in advance, and it might increase total travel time delay. And then the detection range we can manipulate by simply just lowering the range at which, or the point at which we detect the vehicle. And the benefits and drawbacks are similar in the respective minimum distance to stop bar. So our hypothesis, or what we thought would happen, is a large detection range and a small minimum distance to stop bar would result in less delay, because that's more time for the RIO to calculate the most optimal point, and it has the most information to do that with when it has as much information as possible, because we're increasing that range at which it's detecting the vehicle. Now, the conclusions of this project, definitely the RIO is sensitive to different minimum distance to stop bar and detection range values. So that was one of the questions, is was it even a factor in changing delay? And from my experiments, we can definitely say that it is sensitive to that, and there might potentially be an optimum value. And based off my experience, my experiments, that value is probably in the 30 to 40 meter range for Gale Stadium intersections, which is a little bit higher than what we were expecting, probably expecting more in the 20 to 30 range. And I'll get to more on that in the last slide, because another important factor was that the travel time delay also decreased with smaller detection ranges. So in essence, it was the reverse of what we thought would happen. It wasn't totally small, but it wasn't exactly the largest detection range we could have had possible. So overall, it seems that the RIO performs better if it has if the least amount of calculations it has. So what I suspect is happening is the more time it has, that means the more time it has to push the vehicle farther back. So this could be a problem if there's lots of vehicles in the simulation and it has to figure out the best way to go through. What it's doing is, since it's giving trajectories every second, that gives it more time, in essence, to delay the vehicle and push it farther back. Now, it is true that if it doesn't have enough time, it probably will send not a very optimal trajectory at first go. So there is an optimal range in there that I think can be explored further in future research. Now, as for me and my future after this experience, this experience has been great. Surf has been a great experience. I've learned a lot about Florida and what it would be like to pursue a PhD here, and also just more about transportation engineering in general. And I definitely want to pursue a PhD in transportation engineering, and I definitely will be applying to the University of Florida. It's provided a great experience for what a PhD would look like, and a great way to compare other schools as I continue my graduate school search. And my primary interest is in intersection optimization, and the different characteristics of that are geometric design, so roundabouts or signaled intersections. How do autonomous vehicles play a role? How can they improve mobility at intersections? How can connected vehicles improve mobility? And then also in mixed environments, how can we better predict human factors and human driving behavior in order to optimize and reduce travel time delay at intersections? And then, of course, I want to continue to develop my Python skills. This slide shows some acknowledgements and some links below to see more about what I've worked on, and then just some people that have really helped me out in the projects. And I definitely couldn't have done a lot of this without them. So I appreciate their help. And thank you for watching this video, and I hope to provide more updates on my work in the future. Thanks.